Okay, perfect. So now we are going to have our last session, which is the contributor talks. We are going to have 6 interesting talks here, and we are going to start with the first one. But just to let you know, you can ask all your questions at the end of each talk, either by raising hand and opening up your mic, or you can just write it in the chat so you can ask your question from the speakers. So the first talk is called NeuraCrypt is not private, which the speaker is going to tell us how they could attack this NeuraCrypt library. Saeed Mahloujifar is going to speak for us, and the floor is yours. Saeed, start please.
Thanks, Sahar. Do you see my screen?
Yes, perfect.
Great, thank you very much. I'm Saeed Mahloujifar. I'll talk about our work. NeuraCrypt is not private. This is a joint work with Nicholas, Sanjam, Somesh, Mohammad, and Florian. All right, let's start. Let's start with the problem setup. So we have 2 parties, Alice and Bob. Alice has access to a data set. Bob has access to a learning algorithm and the computational power to run that learning algorithm. Alice wants to use this learning algorithm to get a model, but she doesn't want to send the data in plain. So she first encodes her data using some encoding scheme that potentially takes keys and sends this data set to Bob. Bob trains the model on this encoded data and sends the model back to Alice. And now Alice can use this model in a very specific way. That is, before feeding the instances to the model, she has to encode it with the same key, and only then she can expect to see the right output. We call this primitive private learning with instance encoding. And NeuraCrypt is a recent proposal that tries to achieve this primitive through encodings by random neural networks. So let's see how it works. It basically only introduces a new encoding algorithm that uses neural networks, and it doesn't change anything about the learning algorithm. Learning algorithm is a typical learning algorithm that we apply to neural networks, but before doing that, you use their encoding scheme, which has 2 procedures, the key generation and encoding. The key generation just samples a neural network with random weights, and that will be the key. And when you want to encode, you just run your input on this random neural network. So this bottom picture has the exact architecture of the NeuraCrypt. It has some other details like the random permutation at the last layer, but you don't have to worry about that. You can just think of this as a neural network with random weights. So what is the privacy definition here? So they define the notion of perfect privacy, that is saying for any 2 instances or images with the same label, you expect the distribution of the encodings to be exactly equal. And the distribution is taken over the different keys. So when you change the key, you expect for any 2 cats distributions of the encodings to be exactly equal. This is the privacy definition. How do they analyze this, their encoding? So they first show a proof of concept encoding called ideal encoding that does the following. So it takes an instance and maps it to another instance with the same label. For example, it takes a cat image and maps it to another cat image in the space of all possible cat images. So they show that this scheme can actually achieve perfect privacy, and it could also be used for learning because you are preserving a lot of good information. You are just mapping a cat to another cat, so it should be still learnable. And at the end, they claim that NeuraCrypt approximates the ideal encoding. So this is the intuition behind the privacy of their scheme. So to back their claim, they provide 2 challenge datasets. The first challenge is a combination of 10,000 images with their encodings, and they ask the community to match these encodings to the plain images. They also have another challenge that I don't want to talk about it here, but I'll get back to it a bit later. So in our paper, our contribution was to, first of all, break challenge 1. So we show that with 100% accuracy, you can match the images with their encoding in the challenge dataset. We also instantiate this challenge with our own dataset, and we get the same result. So this shows that NeuraCrypt is not does not have the perfect privacy and is not an approximation of the ideal encoding. In a high level, the idea behind our attack, the high level intuition is that we use the statistical invariance in different layers of a random neural network. For example, if you look at the mean of the pixels in the image, you expect a particular behavior as you go through the different layers of the network, specifically when your weights are selected at random. We use this intuition and design our attack to match the final encodings and the inputs. And we do it specifically in 3 steps. So the first step of our attack, we train an embedding that its goal is to map images and their encodings to almost the same point in the embedding space. So we want the embedding of the image and its encoding to be close to each other. But for any other image, we want the embedding of it to be far from the embedding of the original image. So this is the property that we want in this embedding. We do this by training a neural network using standard loss functions for this goal. But before that, we calculate the moment vectors of these images and give the neural network some hints of where to look at. So we just ask the neural networks to just look at this moment vectors, the mean, the variance, and up to ith moment, and calculate the embedding just based on this. And this is why I call it a statistical invariance, because what the embedding is doing is basically finding some invariance in this statistics. So in the second step, what we do is we use this embedding that we trained on our own data set to find some similarity metric between all the pairs of encodings and images. And after we do this, we just solve a maximum matching problem on the bipartite graph, and that will be our final match. And as we show, this attack obtains 100% accuracy. All right, so what about challenge 2? So I didn't tell you what challenge 2 was. Challenge 2 gives us the encoded dataset and asks us to find an approximation of the neural network that was used to create this encoded dataset. And approximation is done in a very specific way that is based on the nearest neighbor match in the encoding space. So this, we don't find challenge 2 to be an interesting challenge, first of all, because it's a ciphertext only challenge and it restricts the adversary too much. We believe this is not a good definition for privacy. And it's not clear how this definition and how this challenge is related to privacy. At best, this challenge is analogous to a key recovery challenge, but we don't see why it's necessary to break this to show NeuraCrypt is not private. In particular, we actually make this formal and we show a encoding scheme that is provably secure in challenge 2, yet it reveals the whole input in plain. So we could try for years to break the challenge 2 for this encoding and be unsuccessful, but it's clear that it's broken. So this is another reason that we don't study this challenge 2, because it's not necessary to show NeuraCrypt is not private, and we already have a strong attack that shows it's not private. All right, so now you might ask, what about the ideal encoding? They had this ideal encoding that they analyzed and they showed it's has the perfect privacy. Can something else approximate it? NeuraCrypt doesn't, but can something else approximate this ideal encoding? To answer this question, we have a formal impossibility result here saying that if you can approximate the ideal encoding for some concept function C, then there is an Oracle PPT algorithm that can extract this concept function from this encoder by just querying the encoder. So what does this theorem mean? It means that the encoder must already know the concept function, which makes it like there is no point in learning C from data. You could just learn it from your encoder. So either the encoding is impossible or learning the concept function itself is kind of trivial. All right, so the proof idea here has 3 steps. So the first step, we use the encoder to sample a data set of points. We take one cat, we take one dog, we use different keys to generate our own data set. And then in the second step, we use this data set to train a classifier that gets some non-trivial accuracy on this distribution. And in the third step, we use this classifier and we use this boosting idea to make the accuracy of this classifier almost 100%. The reason we can do this is, again, because we have access to the encoder that can distribute the error across all points. So given a point X, I just sample a bunch of keys and encode the X based on those keys, feed it to the classifier and take the majority vote. And you can easily show that this gets very close to 100% accuracy. Okay, to summarize, we show that NeuraCrypt is not private. It doesn't have the perfect privacy that it claims. We show that challenge 2 is not much relevant to privacy. And we are, at the end, we show that the approximation of the ideal encoding is basically impossible. That was it. Thank you very much.
Thank you very much, Saeed. Please, if anyone has any question, raise your hand or unmute yourself. Okay, thank you, Saeed. So we can move on to the second talk, which the topic is secure Poisson regression. And Mahimna Kelkar is going to show us how we can compute Poisson regression into two-party secure computation. Mahimna, take it away.
Thank you. I'm gonna share my screen. Can you see the screen?
Yes, perfect. Start.
Okay, awesome. So I'm Mahimna, and today I'll be giving a talk on our recent work on secure Poisson regression. And this is joint work with Phi, Mariana, and Karn. So privacy-preserving machine learning has been kind of a very active research area, as evident by workshops like these. And a lot of the previous work has focused on efficiently learning different types of useful functions in a secure setting. So some common functions that we've been usually thinking about have been like linear regression, where the goal is to jointly learn a linear function, or logistic regression, where you want to learn the probability of a binary response variable. There's also been significant progress on learning more complex functions like neural networks. So in this work, we want to focus on another common model used in practice that has not been explored in the privacy-preserving computation literature so far. So we'll look at Poisson regression, for which the goal is for the parties to jointly learn a Poisson model without revealing their inputs. And our emphasis will be on efficiency of this secure computation. So what is a Poisson model? Poisson model is used to model count or rate-based data. So this is usually modeled by the function of expectation of y given x equals e to the power dot product between theta and x, where y is the response variable and x are the predictor variables, and theta is the weights vector. There's also times where you have another variable called t, which models the exposure for different inputs, which is what's used to model the rate-based instead of the count-based data. So Poisson models have actually been used extensively in the past to measure, as I said, count or rate-based data. So for example, in medicine, they've been used to predict mortality rate or susceptibility of diseases based on age or gender, pre-existing conditions, or habits like smoking or alcohol use. They've been used in politics to understand voter turnout and engagement based on demographics or news exposure. They've been used in finance and lending to predict credit default rates based on income, or more recently in advertising to model click rates for online ads. But in all these use cases, there's a lot of private or sensitive information that's used in the training of the Poisson model. So for instance, we could have sensitive medical or demographic information in this training set, which we don't really want to reveal. So the goal for us is to try to learn this Poisson model without revealing this sensitive information. So we focus on the semi-honest two-server model. We have two servers, A and B, that have shares of the training data. So the data D is split between two servers as the shares DA and DB, and these are given to the two servers. And now the goal is to jointly train a Poisson model. So the data here will be given in a fixed point ring parameterized by three parameters, L, F, and H. So all the values are given in a fixed point ring Z2 to the L, and the fixed point numbers are represented with F fractional bits, and the absolute value of all of the numbers that we work with is less than 2 to the L minus H. And this is done to have a gap between the representation of the fixed point numbers and the overall ring to reduce the probability of errors. So more formally, for our Poisson regression problem, we have a training data where we have n data points, and the ith data point is given with m variables, and ti is the exposure and yi is the response variable. So we can also represent them using matrices, and now we want to learn a weights vector theta such that each yi is approximately ti times e to the theta x. And unfortunately, exponentiation is quite difficult in MPC, and usually any kind of nonlinear function is the most challenging and probably the bottleneck. So here we'll need to compute fixed point exponentiation, which is usually hard. And so one of our contributions is a very efficient protocol for secure exponentiation. So this surprisingly makes it so that it's no longer the bottleneck of the Poisson regression function. So in practice, to do this Poisson regression, the natural choice is to use gradient descent to learn the weights. So we start with this loss function, L of theta given the data, where for the minimization, we've computed the gradient of the loss function as the gradient of L of given theta is like the sum of how much the error is between the learned weights and the actual function. And of course, we can represent this using matrices again. And now the gradient update function is as follows, where the k plus 1th iteration will learn the weights as theta equals 1 minus beta times the previous theta plus alpha times this gradient of the loss function. And here alpha is the learning rate, which is helpful to tune for better conversions. And beta is a regularization parameter, which is used to prevent overfitting. So this is pretty standard from taking from just Poisson regression and trying to understand what kind of gradient updates we need to do or replicate in the secure setting. So in our work, we'll make the following contributions. First, as mentioned before, we'll give a very efficient protocol for secure fixed point exponentiation in this semi-honest two-party setting. Second, we'll provide an optimized secure matrix multiplication that specifically benefits our setting by amortizing the cost of multiplications over many of the iterations of the gradient descent. And finally, this results in a highly efficient, secure Poisson regression protocol. So I'll very briefly describe our secure fixed point exponentiation technique. So it's split into so here's the high-level technique. The first thing that you do is you split the exponent into fractional and integer parts. And the second thing that you do is you exponentiate both parts locally. So you exponentiate the integer part separately and the fractional part separately. And then you combine to get approximately multiplicative shares of the final computation. So here, the integer exponentiation can be done using Fermat's little theorem. So it'll give you shares in a field FQ rather than the fixed point ring. And for the fractional exponentiation, we have a new technique where rather than using standard polynomial approximation, we can enable the parties to compute the fractional exponentiation locally by exponentiating in real numbers or floating point, and then combine it with the integer exponentiation also completely locally. And since the computation is local and you're using floating point or real numbers, this actually makes the error much smaller than polynomial approximation. And finally, now we can take these multiplicative shares and convert them to additive shares using only one round of communication. And this is the only communication step that will be used in the protocol, and only requires sending a single field element to be communicated per party. So just to compare our exponentiation protocol a little with other techniques, as I mentioned, the error is much smaller than polynomial approximation. It's usually at least a couple orders of magnitude smaller, and the gap widens the more fractional bits that you use for the protocol. We also have a very efficient online phase where the communication is just one field element per party. And here FQ is a L-bit prime. Q is an L-bit prime, so the field is roughly the size of the fixed point ring. So for the online phase, we have 1 microsecond when we're using a 63-bit ring, and 55 microseconds for when we're using a 127-bit ring for the exponentiation computation. We also have a huge advantage when it comes to pre-processing. So our pre-processing is only for the multiplicative to additive shares conversion, which only takes 2 elements in FQ compared to several megabytes using other techniques that rely on bit decomposition or polynomial approximation. So this means that even in like an online only setting, the performance will be very good where you can't do pre-computation earlier. The second technique we'll use is what we call correlated Beaver triples. So briefly recall that multiplication or Beaver triples are used as pre-processing to compute multiplication of two shared inputs, and these can be easily generalized to matrix multiplication. So now if you look at the loss optimization function again, you'll notice that there's in each iteration, you have one multiplication with X transpose and one multiplication with X. And these are kind of used for each iteration, and the X's are the same and just the thetas change. So basically for the ith iteration, we have a multiplication of the form X times Zi, where the Zi's change, but the X remains constant. So now with this observation, we can do something clever. So instead of using standard matrix triples as pre-processing, we can use these correlated triples since one of the matrix is constant. It does not need to be shared again. And now this means that the reconstruction phase for the multiplication needs to be only done once for the first matrix, and later iterations can reuse this. So now the communication cost can be amortized over many iterations because the cost of doing many iterations is only slightly larger than that of one iteration. And typically, since we're doing hundreds of iterations of the gradient descent, the efficiency gains are quite substantial. So as a conclusion, our Poisson regression only takes 4 rounds for the entire protocol. And if our data set does not contain an exposure variable t, then we can shave off an additional round. So it only takes 3 rounds. And we can also use the same protocol for secure inference. So as a comparison of our secure protocol to plaintext regression, we plot how the weights change for different data sets compared to secure versus plaintext. And the lines for secure and plaintext regression in these graphs are essentially identical. So I'll say like the root mean square error that we computed between the plaintext weights and the secure weights is less than 10 to the negative 3 or 10 to the negative 4, depending upon what learning rate we use and the data set we use. So this is saying that our secure weights that we learn are very close to the weights that are learned by just the plaintext regression. In terms of just a brief data point for the protocol cost, for a data set with 10,000 training samples and 100 binary predictors, the amortized cost over 100 iterations is 1.35 seconds per iteration. Online cost is 2.88 seconds and 1.3 megabytes of communication per iteration. So the total cost over something like 100 iterations is a little over 2 minutes for offline phase, 5 minutes for online phase, and about 136 megabytes of communication. And I'll sort of end with that. Here's a link to the paper in case you're interested. Thank you.
Thank you very much, Mahimna. It was a great talk. I don't see any questions in the comment part, but if you have any questions, please ask.
I think there's a question. Someone's raised their hand.
Yeah, it's me. Just a quick question. Thanks a lot. I just would like to ask, is the method that you designed for exponentiation is very specific to 2 parties and passive security, or can you extend it like very easily?
So it's relatively straightforward to extend it to n parties because the only thing that needs to change is the multiplicative to additive shares component, which can be generalized. It is a little unclear how to do it with malicious security, because one of the advantages of our approach was we can exponentiate in like real numbers locally and then combine. So it's hard to prove a correctness of that using generic techniques. So it's unclear, but it's an open question for malicious security.
I see, thank you.
Okay, great. So thank you so much again, Mahimna. We are going to start with the next talk. Next talk is called Muse, Secure Inference, Resilient to Malicious Clients. We're interested to hear about that. Pratyush Mishra is going to give a talk, so please start.
Hi everyone, let me just share my screen.
Okay, perfect.
get started. So hi everyone, I'm Pratyush and I'll be presenting Muse, which is a protocol for secure inference of neural networks that's resilient to malicious clients. And this is joint work with my excellent co-authors, Ryan, Akshay, and Raluca. So what's secure inference? The problem of secure inference is developing a protocol for a client and server to interact to obtain a neural network prediction. The client has some input X and the server has some neural network model M. And the goal is that the client and server should learn only the prediction M of X, so that the client does not learn anything about the server's private model weights, and the server doesn't learn anything about the client's private input X. So this is many applications for a lot of cases where both X and M can be sensitive, such as home monitoring or baby monitoring or other applications. So as a result, there's been a lot of work over the past past few years on secure two-party inference, and these have a variety of efficiency and security properties. However, like all of these protocols, we can basically classify them into two quadrants. Either you have protocols which achieve very strong malicious security, but have relatively slow performance due to the use of generic subprotocols, or you have protocols which achieve very good performance on state-of-the-art neural networks, but which only achieve semi-honest security. So ideally, what we want to do is we want to develop protocols which lie in this bottom rightmost quadrant. That is, they achieve both malicious security as well as good performance. But malicious security is usually very expensive. So let's take a step back and see if we actually need full malicious security. So in the threat model of secure inference, what you have is that there's usually only a single server which has the model, but there are possibly many clients which interact with the single server, right? And these clients have different kinds of setups, incentives, could be operated by different people, right? And furthermore, the clients can oftentimes easily remain anonymous. Like I can just sign up with a new account for an application, for example, right? So in this setting, it maybe makes sense to consider a slightly weaker threat model, where we only try to prevent malicious clients. We allow the server to be semi-honest, but we allow the client to be malicious, right? So we protect against fully malicious clients. And this makes sense because in this threat model, at least, right, it's much easier for the client to cheat. You can just spin up a new client very cheaply. But if the server gets caught cheating, then there can be heavy repercussions. For example, people might just stop using your service if you get caught cheating, right? Okay, so in this, this client malicious security model seems to make sense, and indeed it allows us to construct much more efficient protocols than would be possible in the fully malicious case, as we'll see. So in particular, in this paper Muse, we provide two contributions. First, we show that existing semi-honest secure inference protocols, including the state-of-the-art ones, are vulnerable to a very powerful model extraction attack that is much more efficient than prior attacks. And this is enabled by the fact that they're using the secure inference protocol. And then we develop a new secure inference protocol that is secure against malicious clients and achieves good efficiency. In particular, it's not vulnerable to our model extraction attack. Okay, so let's quickly go through each of these contributions, beginning with a quick recap of neural networks. So in neural networks, you have alternating, in particular, convolutional neural networks. You have alternating linear and nonlinear layers. The linear layers consist of, for example, of convolutional layers, fully connected layers, average pooling layers, and so on. Meanwhile, nonlinear layers, the most popular one, and the one we'll consider in this talk, is the ReLU. So ReLU is 0 when the input is negative, and the identity function when the input is positive, right? And looking slightly ahead, what makes model extraction attacks often difficult is the existence of these nonlinear layers, right? Without them, the network would simply be a linear system, which is fairly easy to recover just by querying it a number of times, right? Okay, so a quick recap of model extraction attacks. So in model extraction attacks, what we want to do is you have a malicious client which makes specially crafted malicious queries to the server. And then the client uses the responses from these special queries to learn information about the model, so that eventually, after making enough queries, it can construct a rough approximation of the client's, of the server's model, right? So this is problematic for our secure inference case because we don't want to reveal information about the server's model, right? And indeed, like so far, like all of the attacks that have been explored generally have been black box attacks, where the client simply makes input-output queries. So yeah, it only gets input-output access to the model, right? And the question we want to ask is whether the fact that a client or whether the secure inference protocol is being used, can that fact just enable new model extraction attacks? And I won't go into the details here, but basically what we show is that by leveraging properties of a particular class of protocols which rely on additive secret sharing, we can actually construct very new, very powerful attacks that basically eliminate the nonlinear layer entirely from the network. And in summary, what this allows us to do with our new attack is get a much lower query complexity, so up to 300 times fewer queries. We are able to extract the model weights perfectly, rather than approximating them. This is up to floating point error. And we scale with the number of parameters in the model, not the depth of the network. And to get put together, this allows us to evaluate our attack on networks which are 100 times deeper than prior work and which have 60 times more parameters, right? So maybe we're getting up close to deployed models, right? And this is just enabled by the fact that this class of secure inference protocols, they have a semi-honest structure which allows basically the malicious client to malleate its messages. All right, so let's see if we can solve this. So what we do for that is we construct Muse, which is a system for secure inference on convolutional neural networks, which achieves strong security against malicious clients. It supports arbitrary ReLU-based convolutional neural networks, and finally achieves much better performance compared to existing alternatives, which rely on maliciously secure protocols or subprotocols, and whose online phase is very similar to existing semi-honest protocols. So you pay most of the cost of this client maliciousness actually only in the pre-processing or offline phase. All right, so the starting point for our protocol is a prior secure inference protocol, which is semi-honest, called Delphi. So Delphi, there are two phases, a pre-processing phase and an online phase. And the pre-processing phase itself divided into two components. First, the client and server interact to pre-process the linear layers, right? And this produces some material. Technically, underneath it, you use some homomorphic encryption to compute correlated randomness, right? So once they get the linear pre-processing done, they can go ahead to compute the nonlinear pre-processing. And this basically involves the server gobbling some circuits and the client obtaining labels for those circuits. And these labels correspond to the output of the linear pre-processing, right? So basically, at the end of this step, the client and the server, they have pre-processing material for both the linear and the nonlinear layers in the network. Then during the online phase, when the client has its input X, the client and server, they can use their pre-processing material to go ahead and complete the inference and obtain the prediction. Right? Okay, so that's Delphi, right? Let's see what a malicious client can do in Delphi. First, during the pre-processing phase, it can act maliciously to generate some incorrect pre-processing material. So this is illustrated here by the red, right? So you can compute the CL prime and CN prime. And then during the online phase, you can use this, again, you can act, the client can act maliciously to deviate from the protocol and maybe compute some malleated output, right? So what we need to do actually is two steps. First, we need to ensure that during the offline or pre-processing phase, the client follows the protocol. And then we need to make sure that the output of that pre-processing is what is fed into the online phase, right? So we need to commit the client to the pre-processed state and make sure that these are consistent between the offline and online phases. So let's see how we can do that. So first, for the linear layers, it's a pretty straightforward idea. We attach an information theoretic MAC only to the client's linear state, because remember, the server is semi-honest, so we don't need to authenticate the server state. So the server generates a MAC key, and then this is used to authenticate the client state. And then you proceed as before, computing the nonlinear preprocessing, and you feed these two components into the online phase. And the idea here is now because the linear state is authenticated, the server can use the MAC to check the consistency of the output of the offline phase with the input to the online phase, right? And furthermore, for the nonlinear layers, basically garble circuits, they already provide malicious security against malicious evaluators, right? So if you make the client become the evaluator, then we already obtain security against in the nonlinear layers for free in some sense. But actually, that's not quite sufficient, because if you remember in Delphi, we actually feed the output of the linear preprocessing into the nonlinear preprocessing. So what we need to do is actually make sure that these are consistent as well. And we're not doing that right now because oblivious transfer can't actually authenticate this. It can't check that the input is consistent. So to overcome this, we design a protocol for conditional disclosure of secrets, which first checks if the input is valid, that the MAC is correct. And if so, it outputs the garble circuit labels that correspond to the client's input. And then by doing this, basically, we're able to authenticate both the linear and nonlinear layers and obtain security against malicious clients. So that was Muse in a very rapid, I covered it very rapidly. The cool thing is that the online phase is basically equivalent to semi-honest Delphi. There's only a very small overhead. We implemented our protocol. It's available online here. And in terms of evaluation, we compared it against a couple of baselines, both semi-honest and fully malicious. And what we found was that compared to the fully malicious, we have very low overhead, 21x better, and we're only slightly worse than the semi-honest baseline, Delphi. We pay in communication, but I think in the future work, we can try to reduce this. And this is also true for the online phase. Again, we have only a little bit overhead over the semi-honest protocols. Yeah, so in summary, in this talk, in Muse, we developed a new model extraction attack that is much more efficient than existing ones. And then we developed a secure inference protocol that is not vulnerable to our attack, and in particular provides client malicious security. Thank you.
Okay, thank you very much, Pratyush. We have two questions in the chat. Amit's first question asks, how is the honest client supposed to query?
The honest client supposed to query in which case? And the
second question he asks is, isn't CDS just OT plus garbage circuit?
So CDS, actually, we designed a protocol not based on garble circuits. We designed a protocol based on arithmetic and circuit MPC. So in particular, a variant of speeds. That is, we modify it to only have client malicious security, which is sufficient for our application. We could implement it using OT plus garble circuits, but that would be more. We tried actually; it'd be more inefficient. I'm not sure in what context the first question was about, but if it's about the model extraction attack, in the model extraction, like in standard black box attacks, you're just querying inputs, and there's no constraint on what your input can be. Like I, as a client, can make any malicious input. So like there's no constraint there. In our particular attack, the client basically does some undetectable tampering of the share. That's how it works. I can explain more offline if there's any questions.
Okay. Okay, thank you very much. We can start, we can go ahead with the next talk. The topic is Cerebro, a platform for multi-party cryptographic collaborative learning. And Wei-Keng Chen is going to give us this talk. So take it away.
Hi. Hi, everyone. My name is Wei-Keng Chen, and I'm presenting our work, Cerebro, which is a platform for cryptographic-like collaborative learning. And this is a joint work with several of my colleagues. Okay, let me go to the next slide. So the motivation of our work is anti-money laundering. So we have banks that are responsible to predict and prevent money laundering. And they want to use machine learning model to detect them. But this is actually quite challenging because actually each of the money transfer usually involve two banks. And one single bank doesn't have all the information that is necessary to do this prediction. So one good idea is that maybe we can have many banks to train a model using their joint data set. But in the real world, this is quite challenging just because banks have many reasons that they cannot share the data due to privacy concerns, regulation, and probably competition. And so the question is simple, is that how to enable this organization to share data for learning a model without showing the data. And people here already can guess the answer is to use secure multi-party computation. And our work, Cerebral, is trying to have developers who are not expert in cryptography to use secure multi-party computation. Okay, so how can we help the developer? What are the challenges that a developer are facing today? So we find that the first thing that a developer might find challenging is how to choose the right protocol and implement that algorithm efficiently. And now let's assume that we have a developer who has a very good learning algorithm. The first question that the developer need to answer is, well, should I implement the algorithm using Boolean MPC protocol or arithmetic MPC protocol? We know a little bit more about MPC. We know that well, they have some trade-off, but unfortunately, the developer doesn't know this trade-off. And if we explain this trade-off, it's also very difficult for the developer to figure out the differences between them. And the debate between Boolean and arithmetic is just the beginning of the story because there are so many protocols for Boolean and arithmetic, and we know that they perform very differently. For example, we have some heuristic, for example, we know silent OT is good when you have a slow network, and low gear is very good when you have lower number of the party. But once again, our developer doesn't know this. And in the real world, what may happen actually usually is that the developer who is an expert in data science, but probably not an expert in cryptography, implement the same protocol in different platforms and to measure how slow they are. And then they will learn the same lesson that we show here, but in a very painful way. And moreover, in the real world, actually in a lot of the learning algorithm, some of the computation can be done local. That is, it doesn't need to be inside the MPC. And if you are training the model in a semi-honest setting, this is a very important opportunity that you don't want to miss. But once again, the developer might not be able to figure out what is the right local computation to do. And so Cerebral provide a compiler that try to help the developer. And actually two ways that we have that. Firstly is that well, our compiler can firstly using information flow to see which variable in the learning algorithm is visible to some party. And by doing that, we can split the program for the developer into a local one. So it doesn't need to go to the MPC. Second is that we will estimate the cost of different options to run the MPC protocol. And we will choose the best one for the developer. And this is not a simple decision because whether protocol is faster or not actually depends on many factors, including whether you have good network, whether you have a lot of computational power. One example is that if you are thinking about silent OT, but you also have very good network, maybe you will just do non-silent and classical OT instead. And actually we have some observation. Sometimes this compiler can tell you something that you don't know. So let's look at this figure. The first observation that we can have is that, well, it's really important to choose the right protocol because there is a performance gap that's actually not small. And second, some of our heuristic on which protocol is better might not be always true. In this figure, which we actually evaluate a 10-layer decision tree in the semi-honest setting, you can see that when you have more party, suddenly arithmetic protocol become faster than the Boolean one. And then we solve another challenge that like some of the developer might also face in developing like efficient protocol. In real world, when we are doing training, we may actually have basically party might not be the same. And especially they might not have the same network condition. Now let me give you a specific example. Let's consider that like we are doing a global MPC. We have two parties who are in the US, and they have very good network between them, low latency and very high bandwidth. Unfortunately, we have the third party who is far away from them, and the network between them is very slow, which means that the latency is very high, and also the bandwidth is quite slow. And this is a very challenging situation today for our MPC. And let me just give you a specific example. If we are doing the semi-honest version of the speech protocol, a significant part of the offline phase is actually to broadcast a lot of the ciphertext, and then the party will sum this ciphertext up. And as you can see, because party 3 have slower connection with everyone else, it means that like, well, actually party 1 and party 2 will be waiting for the party 3 to finish. And this like will just slow down the entire computation by the slow disconnection. And in our work, Cerebral find out that there are ways to have the party 3. And our idea is that we try to send and receive less data to and from the party 3s. The first thing we can do is that let's send less data to party 3s. If we are like broadcasting ciphertext, but they will eventually be summing up together, maybe party 1 and 2 can sum them up first, and then just send one ciphertext to the party 3 instead of sending them individually. Second, we can let the party 3 send less data to the party 1 and 2 by doing some sort of forwarding. And the idea is that, well, if party 3 need to send the ciphertext to party 1 and 2, let's just have the party 3 send it to party 1, where party 1 forwarded to party 2. And we did an experiment which actually showed that this will give you an improvement. We did an experiment with 12 parties located in 2 different regions. Inside the same region, they have very good network. But between these 2 regions, there is a very slow connection. And we found that like by just using this optimization, that you try to not send too much data in the slowest connection, you can actually get a very significant improvement in the like computation. And we as Cerebral also have other components that I don't have time to describe. You can see our paper for like our domain-specific language. We have some release policy that have ensured parties incentive. And we also have an auditing framework to try to have cache party who provide like bad data to the training. And we also have released a lot of our code. And if you are working on this area, we actually implement a lot of the example program for machine learning, and which might be quite helpful. And in the end, I want to tell you a little bit of some of the open problems that come to our mind when we are developing like Cerebral. And as you can see from like the previous figure, our a very good like opportunity is that we mix different types of the protocol together. We have so many wonderful words in the recent year about mixed protocol computation. Cerebral doesn't support such computation. It have to choose one of the protocol, either arithmetic or Boolean. And this, we are losing a lot of the opportunity to get better performance. So open problem or a future world that people might actually will quite be very useful is that whether we can have a compiler that automatically split the program into different circuits. And you also have an optimizer that actually try to lower the cost. This is not trivial because you now involve the conversion, and conversion have an overhead. It's not just to decide whether convert or not. It's also, you need to decide when to do the conversion. And another open problem that some of the audience might already know that is that our protocol for the network planning, which try to have the party 3 who have a slower connection, only work in the semi-honest setting. And we don't know how to do that in the malicious setting. We know that it's challenging because that in the malicious setting, party often need to send out some sort of proof of plaintext knowledge to ensure that the plaintext are encrypted correctly. And also you need to prove that the party 3 actually aggregate the ciphertext correctly. and we don't know how to do. Idea that seems to work is homomorphic like commitment, but it must be efficient enough. Otherwise, it will become the performance bottleneck. And okay, and that's all I have. And thanks everybody for listening. And I think there is a question in the chat. I will take a look. Number of training sample in serial learning. So the compiler actually need to learn some of the information about the data set, because that can also like influence how the decisions are being made. Yeah. Okay. Any other questions?
Yes, I guess Daniel.
Yeah, it's going to be super quick. Thank you. So just to be sure, I'm not sure I got it. Like the full implementation you have after it compiles the code that you provide as input, does it give like recommendations on what to execute, or does it actually provide the full execution environment to run the proper MPC protocol?
Actually, it's very close to that, because so one very good thing about the Cerebral is that the domain-specific language allow you to write in one Python file, and then you can compile it to both the Boolean one and the arithmetic one, so you don't need to write the program twice. When the cost like estimator tell you which one seems to have a lower cost, you can then go ahead and compile that into that format, and you don't need to rewrite the code. So it's very close to that.
I see. Thank you.
Okay, so if there's any other questions, so we can go ahead with the next talk. The next talk will be called Privacy Preserving Machine Learning for Support Vector Machines. And Hernan Vanegas is going to give us the talk. I would like to actually welcome Hernan to the research community, and especially MPC. I know that you're finishing up your bachelor degree, so kudos to you. And the floor is yours. Take it away.
Thank you. I will share my screen. Do you see my presentation?
Yes, I see that.
Okay. Let's start with the... Okay. Hi, my name is Hernando Vanegas. I will be talking about privacy preserving machine learning for support vector machines. In particular, I will be talking about how to use multi-party computation to train support vector machines. This work was done jointly with Daniel Cavacas and Daniel Escudero. At this moment, we are working on a full paper that will contain all the details of this work. Our contribution is divided in 6 parts. The first contribution is that we implement 3 SVM training algorithms securely with the MP-Speed framework. Second, it is important to mention here that it is a full-fledged implementation. Second, we discuss the precision and the scalability of the secure implementation using the fantastic protocol. We place a special attention in the impact of the fixed point in the quality of the model, for example, in the accuracy and also the training time and the data sent. We compute some upper bounds for the least squares approach that are critical to avoid the overflow when we use fixed point representation. We train an SVM with real-world data to analyze the viability and the scaling of our solution. And finally, we obtain an accuracy comparable to clear implementation using a floating point representation. In the related work, we found only few works that uses MPC to train support vector machines. Most of the works we use homomorphic encryption or do not carry the whole training process privately. Now, what is the big picture of this work? In the first part, we have a method selection. We train an SVM using the gradient descent algorithm, the sequential minimal optimization algorithm, and the least squares. All of them are implemented in MP-Speed framework. We train an SVM with these algorithms, and we select the best suited method according to some metrics. In this case, the least squares algorithm performs better, and we compute some upper bounds for the least squares algorithm. The importance here is that these upper bounds will help us to compute the number of bits needed in the fixed point arithmetic. Finally, we have an experimental evaluation over synthetic data and real-world data, and we unveil some practical limitations, and we conclude about them. Practical limitations like training time, bit size in the fixed point implementation, and so on. Now, in the training method selection, we have the gradient descent algorithm, the sequential minimal optimization algorithm that is a very well-known method for training supervector machines, and least squares approach. It's important here to mention that in all the experiments of this work, we are training all of our supervector machines locally. It is in a laptop that simulates all the communication between the parties, but in the local host. So we generate an artificial data set with 50 rows and 2 columns, and we found that the gradient descent algorithm is the fastest. But it has some limitations because the gradient descent algorithm does not allow us to use the kernel trick, and the kernel trick is important to find nonlinear boundaries in the classification algorithm. And the sequential minimal optimization is slow due to some heuristic. The heuristics causes some branching in the source code, and this branching slows down the MPSP's execution. So we select the least squares approach because it performs better than this sequential minimal optimization algorithm and has a comparable accuracy. Now, the least squares approach, the core of this method is to solve a linear system of equations presented in the equation 1. To solve this linear system of equations, we select the steepest descent algorithm that is very similar to the gradient descent algorithms with some variation in the steep size. In the line 7, precisely, we compute the steep size, the step size in the optimization step. So let's take a look at this quantity because it's very important. The numerator and the denominator of this quantity depends heavily on the number of rows and the columns of the data set. So it is important to compute an upper bound to avoid the overflow during the training execution. So if we compute an upper bound for the denominator, we found that it is O the n to the 7, c to the 6. So we will use this upper bound, the logarithm of this upper bound precisely to find the number of bits that avoid the overflow. So if we look at this table, we compute some bits needed, the ring size of the Fantastic Four protocol for some number of rows and columns, and we found that for relatively small data sets, there is a relatively high number of fixed point bits needed to avoid the overflow. Now, let's evaluate what happens with the number of rows and the number of columns of this data set. In this case, if we leave the number of columns and we generate multiple data sets with a variety of number of rows, we found that the training time and the data send increases polynomially with the number of rows of the data set. And there is a linear relationship between the number of products and the data set and the training time. So it tells us that most of the time, the training time is spent sending data, and the local computation is spent a low number of a low time. So the most important result here is that there is a similar accuracy between training an SVM securely and training an SVM in a clear implementation using floating point arithmetic. And this fact is not modified if we increase the number of rows. Finally, what happens if we change the number of columns and we leave the number of rows fixed? We generate artificial data sets to do this, and we found that the training time increases almost linear, and the gap between the fifth and sixth columns is a technicality in the MPSP framework with the local computation and the word size for the local computation of the protocol. The accuracy here is not affected as well as in the rows experiment. Finally, and maybe one of the most important results here is that what happens if we leave the number of rows fixed, the number of columns fixed also, and we change the separation between the two classes that we want to separate in the data set. We generate multiple artificial data sets for this, and we found that the training accuracy in the secure implementation and the clear implementation is very similar. The accuracy is not affected by the fact that the training is done securely. So it is a good point in favor to the use of multi-party computation to train support vector machines with the least squares approach. Finally, we train an SVM with a real-world dataset, a heart attack dataset taken from Kaggle with 303 samples and 13 features. We train the supervector machine with 70% of the samples and 14 features after some preprocessing. And we use a linear kernel here. So we found that the training accuracy and the test accuracy are very similar. The secure implementation is very competitive with respect to the clear implementation that uses floating point arithmetic. The data sent is high. It took some hundreds of bits, so we will talk about this in the conclusions. The secure implementation took more time than the clear implementation, but it's a very well-known result. It's a trade-off between security and time. So in the conclusion, we have that the accuracy is not affected by the fact that the training is done securely. This is an important result, and we see this with artificial dataset and real-world dataset as well. Most of the training time is spent sending data, as we see in the rows experiment. And finally, the number of bits and the ring size of the Fantastic Four protocol depends heavily on the number of rows and columns. And we must take care here because if we use another kernel rather than linear kernel, for example, a polynomial kernel of degree 3, we have that the upper bound is increased in a considerable quantity. This is a problem because it will increase the training time and the data sent during the protocol execution in the least squares approach. As a future work, what happens if we use a small fixed number of bits and we use it wisely in order to compute the operations that cause an out of range operation of an overflow in the least squares algorithm, and this will help us to attack the problem of the increase of bits. And all experiments here were executed locally. What happens with a more realistic environment, for example, a distributed network, when we consider a bandwidth and other things like the data sent that took some hundreds of gigabytes, and the training time will be affected as well. Thank you for everything.
Okay, thank you very much, Hernan. Since we are having a lack of time, let's next move to the next speaker. The talk would be about improved multi-party fixed point multiplication, and Hernan or other authors of this support vector machine work, if you can reply to the questions in the chat, that would be great. So Sai Krishna Badrinayaran, if I pronounce your name correctly, so please, floor is yours.
Let me just share my screen. Can you see my screen?
Yes.
So thanks for the introduction. My name is Sai Krishna. Welcome to my talk. I'm going to be talking about improved multi-party fixed point multiplication. And this is joint work with Isa, Pehan, and Peter. So first, let's look at machine learning training, as all of you are aware through all the talks today. Typically in training, we have data that is stored across multiple different sources. And each party could have very similar or even different types of data. And ideally, we'd like more data because more data implies we can train a better model. But unfortunately, due to competitive or regulatory reasons, parties are not authorized to share the data with each other. And so it's not, so we would still need some sort of privacy preserving machine learning training. And a similar problem also arises in the case of inference if we have a pre-trained model that is shared across multiple parties. Right? And as we're all aware, there's a long list of works on using MPC to solve this. Basically, the different parties come together and run an MPC protocol to generate the trained model or to perform inference on the pre-trained model. Right? So much of the prior work in this space of using MPC has focused on the setting of 2, 3, or maybe 4 parties with at most one corruption. And the goal in our work is to extend this to the n-party setting. So can we design MPC protocols for secure training or inference with a larger number of parties? And a natural question one might ask is, there has been a tremendous improvement recently in designing very efficient general purpose MPC protocols. So can we just use those protocols directly? Unfortunately, it's not as simple as that. As we've seen in previous talks, machine learning typically requires dealing with fractional or decimal values, while MPC works well with modular arithmetic. And so these two don't necessarily fit together. A natural naive idea is, can we just scale the machine learning computation to work with a large enough modulus so that we can do everything over this modulus? And as you might expect, this would fail for if you wanted to perform a large number of multiplications, it would just not scale well enough. And another idea could be that we just perform the fixed point multiplication itself using Boolean circuits and then run our favorite MPC algorithm. Once again, this would also be very expensive, either in terms of number of rounds or communication, depending on which flavor of MPC that we use. And indeed, a lot of the focus in prior work has been on building efficient fixed point multiplication protocols, where we want the inputs and the output to be secret shared amongst the parties. And in our work, the question we'd like to ask is, can we design efficient multi-party fixed point multiplication protocols where the inputs and outputs are secret shared, and we want it to work for larger values of x? Okay. And before I go into the results that we obtain, I'm just going to briefly recall the notion of replicated secret sharing. Maybe most of you already heard it, but just for the sake of completeness, let's say there are 3 parties here, and we want at most one party to be corrupt. To secret share a value x, we just additively split it into 3 components, x1, x2, and x3, and we give each party 2 of these 3 components, right? So P1 gets x1 and x2, and so on. Addition would be pretty easy to perform. You could just locally add your respective shares if you have shares of x and y to get a sharing of the sum. Unfortunately, multiplication is not so simple. You cannot just directly multiply your shares as you might expect. But if you just spend a bit of time thinking about it, you'll notice that multiplication is also not too difficult. If you just wanted to do regular multiplication, each party can compute one of these 3 terms, Ci, locally. So Pi computes Zi locally, sends it to Pi plus 1, and this way parties get their shares. You would need to add some additional 0 shares just for sake of privacy. Right? So replicated secret sharing provides you a nice way to do arithmetic computation, and this can be generalized to any arbitrary n parties, and it's a useful way of secret sharing data if you care about relatively small values of n. For larger n, the number of shares would grow exponentially, so it might not be suitable. With that in mind, let me briefly recap our results. We designed a new technique for share truncation. What I mean is, if you have a sharing of x, and now you wanted to truncate it, or if you think of x as a decimal value, and you want to divide this value x by 2 to the d for some public value d, So we design a new technique to perform this task. And we use this technique to design efficient protocols for fixed point multiplication, where the data is secret shared using several different schemes. So, the first scheme is the first protocol works for replicated secret sharing with semi-honest security. The second protocol builds on the first one and achieves malicious security. And both of these protocols work in the honest majority setting. The first protocol has two flavors. It can be a single round one or a 2-round one. The third protocol is once again in the semi-honest security model with honest majority, but works for shared secret sharing. And finally, the fourth protocol works for additive secret sharing with semi-honest security, but we now tolerate also a dishonest majority of corruption. And then we plug in these protocols to design general MPC protocols where the arithmetic circuits can have addition gates as well as fixed point multiplication gates. Okay. So very briefly, let me show you some comparison of our protocol, the semi-honest protocols with some prior work. Let me use N to denote the number of parties, T to denote the corrupt parties. And let's focus on the replicated setting where let me call K to be the modulus. And so our protocol performs better than the prior work of Mahloujifar and Rindal, where we, unlike their work, we don't have any offline communication or interaction between the parties. The online communication is roughly identical, except we have a minor optimization that allows us to reduce the communication to trade off for more rounds. And then in the context of shared secret sharing, once again, we have a protocol that works identically in the online setting in terms of communication, but we improve on the offline communication cost once again. Here, K denotes the logarithm of the prime modulus. So the takeaway message is that our protocols improve on prior work in terms of better offline communication costs. Okay? And the remaining few minutes I'm going to use to briefly describe the techniques in our replicated sharing based protocol. I'll just focus on the semi-honest setting for now. So let me recall the approach taken by Mahloujifar and Rindal in their work titled ABY3. So the idea is, let's say you have 3 parties and you have inputs X and Y that are replicated, that shared using replicated secret sharing. And you want the output Z, which is approximated as X times Y divided by this public value D. So now in the pre-processing phase, parties interact to generate shares of R and S, where R is random and S is computed as R divided by 2 to the D. Okay, so S is a truncation of R, if you can think of it that way. And so what happens in the online phase? First, parties run the regular multiplication protocol that we saw briefly earlier to compute a sharing of X times Y. Now notice that this sharing needs to be truncated or divided by D. Divided by 2 to the D. There's a typo here. And the idea is that instead of doing the division locally anymore, what parties do is they compute arithmetic or additive secret shares of this product subtracted by this value R. So they compute additive shares of XY minus R and reveal all these shares to the first 2 parties, P1 and P2. Okay. So now P1 and P2 compute their share of the product as Z prime divided by 2 to the D. So their share would be XY minus R by 2 to the D. And then the second and the third shares could just be the truncated shares of S directly. And the idea is that now these 3 shares would now give you shares of XY by D, and it would be very close to the resulting output that you would get for, except with some negligible error. Okay. And as you can imagine, this can be easily generalized to N parties as well, if you just expand on this protocol and make it work for the N party setting. Unfortunately, in the N party setting, this pre-processing is pretty expensive because parties need to interact together to compute these random shares. And the goal in our work is, can we generate these truncation pairs locally without needing parties to interact? And here is quickly the brief idea for non-interactive sampling. Let's say we have a value X that is in the range C2 to the K. Now, instead of generating shares of R in the same space, what if the shares of R were from a larger space? So the idea is if we generate each share of R to be lambda bits more than the space in which X is from. Okay. Now we have a few observations. First, suppose we're working over an even larger space. So let's say we're working over Z2 to the K prime, where K prime is larger than both K and K plus lambda. So now recall that if you, or observe that if you reconstruct R using these various shares Ri, the reconstruction would not wrap around Z to the K prime. And so the distribution of R and R plus X would be statistically close. And since R is lambda plus 2 bits more than R, X. And finally, these shares of R can be generated locally just by sharing PRF keys, right? And once you have these shares of R, you can just locally truncate each share to get shares of R by 2 to the D, replicated shares, and you don't need to interact in the pre-processing at all. So with this idea, let me show how to plug in this idea into a replicated sharing fixed point multiplication protocol. The approach is very similar to what we saw earlier. X, Y, and the product Z would be over the space Z2 to the K, but we'd be working over Z to the K prime, where K prime is larger than K. It need not be significantly larger, so you just need K prime to be K plus 2 lambda plus logarithmic of the number of parties. M denotes the number of shares. So if you have n parties, you would have n choose n minus t shares, where t is the number of corruptions. And so the pre-processing parties just jointly sample some PRF keys, which is not expensive. And it could be done locally. Whereas in the online phase now, just to generate shares of these random strings R, parties locally compute their individual shares, Ri, and each share is at most K plus lambda bits long. And then the rest of the protocol follows quite similarly. Parties compute additive shares of xy minus r. The first n minus t parties get all of these shares. They can then reconstruct to compute z prime, and they set the first share of the product to just be z prime by 2 to the d plus r1 by 2 to the d, where r1 was the first share of the randomness r. And then the rest of the shares of the product are just truncations of the randomness, respectively. Right? I won't have time to go into the details of the malicious protocol, but the protocol sort of builds on this to enforce honest behavior across these steps. And one more thing to note here is we also want to add some zero sharing to ensure privacy of these additive shares. And once again, you can add these zero sharing by using PRF keys and locally generate them. And how do you modify this to a two-round protocol to reduce communication? You just don't reveal every share of these additive shares to all the parties, but just reveal them to one party and have that party compute Z1 and send it to the others. Yeah, I'd like to stop here. Thank you for listening to my talk.
Okay, thank you very much. I guess we are done with all the talks for the workshop. I would like to pass the mic to Antigone if she's available. So I would like to thank all the speakers in the whole workshop and also this contributed talk session. Thanks everyone. And Antigone, the mic is yours. You're muted.